Yeah, good evening, everyone. Switch on your cams. Let's start off. Just give me a second. I just spilled water on my table. I was cleaning. Sure. Hmm. So the next test is online. Loss of motion ka test is online. I'll post the results tomorrow for the kinematics. I think most of you have done well, except one or two people have messed it up, and some of you have not given the test. 3 people are missing the test. Who are these 3 people? 3 people have not given the test. Can you guys say hi, sir? I didn't give the test. I'm great. Who are these 3 great people? You can just raise your hands. Okay, no problems. We will give you a call in the evening. Don't worry. We will say hi to you directly. We call your parents. So you guys are not supposed to miss the test. 3 people have missed the test out of 22. 19 people have given. So please see what went wrong. The tests are important. Don't miss them. Okay, let's start off with a question. Like I said, we'll be having a PTM in the next month, somewhere in the middle of September. I'll let you know. So all the test scores and everything, I'll be dividing you people into based on your performances and all. We'll be having a very positive scolding session. Sorry, PTM, parents teacher meeting. You should not say scolding session. What are we looking at? Kinematics. Shit, why are you doing kinematics? This is a HCV question. Sure, let's get this thing. We're just left with springs and pseudo force. Pseudo force is not much actually. We'll not be doing too much on that. Technically speaking, it is a waste of time, but it's quite useful in circular motion. In loss of motion, we really don't use it much. But we will see few problems on that also. How to do this thing? So we have a weighing machine and the person standing inside the box and all. So before going ahead, tell me one thing. What does the weighing machine measure?
The weight, so the mass.
No, 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 no. There is a, it's not mass. You guys are getting confused. See, what I measure and what I show are two different things. Right, Ronald, Anika. Weighing machine measures normal reaction. Be careful, huh? Look at the words. What you measure and what you show are not same. But shows reading equal to normal by g. So whatever normalization it will measure, it will divide by g and show you. Most cases, when you're not moving or anything, n will be mg, you will get mass. Are you getting the catch? But no, remember, a weighing machine always measures normal reaction. So just to give an example, imagine we have a person kept it in an elevator. Let's say person ka weight is 60 kg and the elevator is going up with 2 meter per second square acceleration. So if you draw the FBD of the man, the normal reaction n mg, which is 600, and acceleration a, we get n minus 600 is equal to 60 into a is 2. We get normal reaction is 720 newtons. So the reading will be, I'll take g as 10, 720 by g, which is 72 kg. Did you see? Even though your weight is 60, because of that lift acceleration, it is showing your weight as 72. The same thing you could have done in the reverse also. The man is standing on this weighing machine, and if the acceleration was down, you can calculate, you'll get n minus 600 is equal to 60 into minus 2. You get n is equal to 480 newtons. So in this case, the reading would have shown 48 kgs. So this is the fastest way to lose weight, right? You need to lose weight very fast. You just get into a lift and accelerate it downward. But it is a temporary weight loss program. But works. Are you getting this? Can you see the mass is 60, but your reading is something else? So this is what a weighing machine does. It measures normal reaction divides by g. Now let's get this question. So that is a concept you should know about a weighing machine. Other than that, the question will be regular. There are two parts in this question. Part one, if the man manages to keep the box at rest, what is the weight shown? What is the force he should exert on the rope to get his correct weight on the machine? Get this 3 minutes. This time?
Yes, sir. Thank you.
Clear? Please have a look at this. Ask me if you're confused. Palaksh, cam on. 15. Yeah, that looks right. But let's see. So now see, if I draw the FBD, you could have done this thing, you can take the whole thing as one system. If you take the whole box as one system, you'll observe tension and tension. And the total weight will be m plus mg, that would be 900. So we get tension is equal to 450 newtons. Now, if you draw the FBD of the man pe force will be tension, the string is pulling up, mass mg, which is 600. And this would be the normal reaction, and this tension is 450. So n would be 115 newtons. The reading will be 15 kgs. So in the first case, that is the scenario. So this is the case when the man is keeping the box at rest. Acceleration is 0, box is at rest. Now the second part. If you want to see the actual weight on the reading, meaning the weighing scale should show the weight is 60 kg. Then with what force should you pull the box? Get the second part, you got a minute. Please ask me, anyone confused with this, what I did? Or you don't like to take the full thing as an FBD, you could have done this also. You can just draw the box ka FBD. Then the diagram would be N, small mg, which is 300. And this is tension. This also works. You could have taken two separate FBDs, or you could have taken full FBD and man ka FBD. So this guy would be T is equal to N plus 300. In this case, you'll get T plus N is 600. You would have got it either way. But this is faster if you take the whole man and box as one system because they're going together. Please check. Clear? What about the second part? Now for the second part, see. It is saying the weighing machine measures the same reading as the mass. So N mg, which is 600. This is the normal reaction, which is also 600. Now think about here, okay? The first mistake what people do now, उनको लगता है अभी भी system rest पे है. Suppose if the system was at rest, now think about it. Then what would have happened? If this will cancel, then tension is zero, right? If tension is zero, won't the box just fall down? So the first mistake here is assuming that A is zero. We don't know. It is accelerating. Because if A was zero, the tension would be zero. There is no one who is holding the box. The box would just fall down. So T is equal to 60 into A. Now, if you just take the box ka FBD, tension, this would be mg, which is 300, and this is A, and this is N. We get T minus N minus mg is equal to ma. T is equal to 60A, N is 600, mg would be 300, and M would be 30A. We get A is equal to 30 meter per second square. And tension would be 1800 newtons. So the man should pull with a force of 1800 newtons. And if you observe the acceleration rate, it is 3 times gravity, 3g that is. The box has to go really fast, vertically. So the mistake what people do, right, they take A as 0 and they try to solve and they don't understand what is happening. You'll get T 0. If T is 0, then this will be 0. Then who is holding the box? You get the meaning? With whatever force you pull the string also will pull you with the same force. Tension is equal to mass into acceleration. Adrit, this mg and n will cancel, na God. Because he said, look at this word. It shows the correct weight. Means what? N is 600, isn't it? Clear with that? Everyone, please check. This clear, na? Yeah. Any doubts on this? Please ask me. It's a good problem. This is a HCV ka problem. I directly took it from there. Neil, Anika, clear? Palaksh, Ali, got this? Holika, Partika, Ritu, Abhinav, Anusha, clear? Can I go ahead?
Yes, sir.
Next one.
Sir, can you show the previous page? Okay, sir.
So we have incline like this. So we have a rope. So we have a rope of linear density lambda. What is linear density? Mass per unit length. Example, if I say lambda is 10 kg per meter, this implies 1 meter ka rope has a mass of 10 kg. This entire incline is smooth. So somehow you're holding this with the force here, tension T, and here the tension is T dash. You're getting it? So you're keeping it at rest. The rope is at rest on this smooth incline, smooth weird surface. The height of the incline is h. This base ka length is L. Find T minus T dash. Find the difference in tension between the string at the top and the bottom if the system is in equilibrium. Meaning, how can I ask you? Meaning, I can tie a block like this. I can tie a block like this. I can ask you find the value of m minus small m. Are you getting? Same thing. So I'm asking you T minus T dash. T and T dash are the tensions at the end. These are tensions at the ends. This is not a massless rope. Rope has a mass. How will you do this? You got an amoeba shape. This is actually an equilibrium problem, but it's a good one. Try. Rastika is very happy today. And that's a good thing. You should be happy. When you're happy, you study well. People have this wrong notion, when I get marks, I'll be happy. When I score well, I'll be happy. Your happiness has nothing to do with this bloody exams and bloody scores. Once you're happy, you will see things in positively. This is I've seen clearly. When I was working in Hyderabad also, we used to have students. There is one guy, whenever exam used to mess up, he used to be positive about it. Like, sir, good thing I messed up now. Imagine the same questions if I had come in the final exam. So he used to take it in a positive way. The other guy used to panic for every damn thing. So because of that, what happens when you go to an exam and you don't get first 3-4 questions? The guy who is positive will think, okay, maybe paper is tough today, so everyone must be struggling. So let me just be more careful and let me search for easy questions and do it. Whereas the guy who is negative, who is panicking, he will see the questions, अरे paper इतना tough है, मुझे कुछ भी नहीं आ रहा है, मेरा rank गया, मेरा life हो गया, अब मैं क्या बताऊंगा सबको? Did you see? The whole thing is negative. What will I tell everyone when I mess up the test? The focus has gone from how to do this test, to what will I explain everyone when I mess up the test. Have a positive mindset. And it is important, like I hope everyone is going for physical activity 1 hour per day. walking, running, some gym, something, I don't care. Take your dog and run with it. But 1 hour, you should be doing a physical activity. That is part of the study. If you're not spending even 1 hour with yourself, again, that 1 hour without music, nothing, you just be with yourself. If you can't even spend 1 hour with yourself, you know what you're telling your brain? I'm not that important. That's a very negative feeling. You are very important. And you deserve at least 1 hour of time with yourself. So do spend 1 hour time with yourself. Anusha, what happens if it's not an equilibrium? First, let's see in an equilibrium, then we will see. Equilibrium आ गया तो वो you can do when it is not an equilibrium. Big deal. If it's not an equilibrium, then I have to give you the length of this curve, which I can't give.
Sir, so the mass of the rope is not given.
Lambda is given the mass per unit length. How do you proceed with this? Let's go. Let's finish all this. We're starting with springs today. Maybe if time permits, we can do pseudo force. Next class, we'll be done with the chapter and we'll be starting of friction next class. Are you guys getting holiday on Raksha Bandhan? No holiday. So
So we
fine.
don't
Even I
have
was
pay
not.
for that day.
Okay. Even I was
So
not
we don't
planning.
have pays on that day. We have college, but we don't.
No, fine. You guys want a off? I won't give you an off, but we can have the class early in the morning, 7 to 9, and we can wrap it up. Think about it and let me know. Or else we'll have in the evening as usual. I don't give holidays anyway. You will get rarely, but so today in the medical batch, I was telling, next Wednesday is a Ukraine Independence Day. We are giving holiday. And people are looking weirdly like, why are you giving for Ukraine Independence Day? And I didn't tell anything. And some of them actually started believing I'm giving holiday for Ukraine Independence Day. Then someone saw the calendar and said, Raksha Bandhan hai. Offline to we give, online we don't give. If pays people are not giving, there's no point. I know for girls it's a very important event. You make a lot of money, but correction time. So let's see how to do this thing. So what we do here, don't take the full string, but take a part of the string. Let's say you take a small piece here. Let this angle be theta. Now understand theta is changing here. Theta is variable. Now if you look at the forces acting on this part, you have a tension T, the lower part of the rope is pulling, and you have a tension here T plus dt, the upper part of the rope is pulling, and you have your own weight here dmg sine theta, and you have this weight another component dmg cos theta, and you have here n. Dm is mass of that small piece. Of length ds. So dm is given by lambda into ds. So if you look at the diagram here, we are taking a small length ds. This is theta. This will be dx and this will be dy. It's a small triangle. I hope you're able to visualize. So here dt is the change in tension due to that small piece. As you go up, right, the tension will keep on changing. dt is the change in tension due to ds. If you keep adding little weight, the tension will also increase little. And theta is the angle of inclination at every point. It changes. So this is the mass of that small piece, huh? I wrote that anyway. So now if you try to, because it is in equilibrium, look at the forces T plus dt will be equal to minus T minus dmg sine theta. There, Anusha, if it is not at rest now, this will be dm into A. Okay. These are the forces balanced. Tt will cancel. We get dt is equal to dmg sine theta. Have a look at this. Next page, we will see how to do this. This is an important model. Right? We'll again encounter this thing, in work power energy and friction. We will see this in 2 other chapters more. This idea of taking a small part of a string and studying it. But you get a pretty nice result. But please look at this, what I did. I took a small part of the FBD because every instant it is changing. I took such a small piece, I can treat it like an incline. The ds can be treated like a incline. Please check. Sure. Can I turn the page? Swastika, Vidyut, can I turn the page? Aditya, Vartika. How is dt changing? Hey, dt is change in tension. D is differential. Dx change in x. That way. Because see now, as you go up, won't the tension change? Let's say if the tension T here, it will be little more, right? So that is what it represents. As you go up, tension is increasing little, T plus dt. Is that making sense? Yeah. So now once we got this, Tt is equal to dmg sine theta. Dm is nothing but lambda ds g sine theta. Now observe this thing. If this is ds, this is theta, this is dy, and this is dx. Dt becomes lambda g ds sine theta is dy. Integrate on both sides. Integral dt lambda into g is constant. You get integral dy. The limits will go from 0 to height h, and this will go from t dash to t. This will give you t minus t dash is equal to lambda g h. We don't know, Anusha. So the science will take care of it. You can take t plus tt, t minus dt, doesn't matter. The science will take care of it. But generally, remember that mathematically, right, we always take the functions are increasing. Always. We always assume functions are increasing, even though we know it is decreasing. The science will take care of it. Okay. So keep that in mind. We always assume functions are increasing. So if you look at here, the result, how we got the answer? So when you took this weird thing, t and t dash with a height h, you're getting the answer as if you have a rope t and t dash of height h. Isn't it? The result comes as if you're just taking a string of a height h vertically. The result t minus t dash, right, is similar, comes out to be similar to having a string of rope h held vertically, independent of the shape. You can have the shape however you want. That's your result. Wait, I'll do one thing. I'll make this diagram even more bad. It's a uniform rope. I'm not able to draw properly. So at this point, if it is T, and if this point it is T dash, basically you're interested only in the difference in height. Are you getting this? The two corners, the heights you have to take. It doesn't matter, the T need not be on the top also. The difference in tension between the two ends will be equal to lambda GH, where H is the difference in height between the two ends, the height. The rope could have been like this also. So now if this was accelerating, the problem here aega, we'll get mass into acceleration, then I need this length of this curve. Initially the string is loose in the second diagram, shown to be taut. Which one? Anika, which one you're talking about? Just unmute and say, no? The red box. No, the string is tight only. The string has its own mass, right? The string has its own mass. So no one is pulling it, but due to its own weight, it is being stretched. Is this clear, everyone? Please check. It's a good one. We'll again encounter this at least 2 more times. And this is how you proceed with this kind of problems. Take a small piece and then integrate. Not a big integration. Clear, Aryan? Any doubts? Others? Anything else? Ali, got this? Ronak? Rehan? Clear? Arjun?
Yes, sir.
Rehan? Clear, na? Venkatesh?
Yes, sir.
Yeah, do keep your cam on, Venkatesh. Others will think I'm showing partiality to you. Bang, I'm totally fine, but people will complain. Mehan might, start a revolt. He's already thinking about it. Next one. Springs. So what are springs? Springs oppose deformation. What is deformation? Elongation or compression is called deformation. And they also springs generate restoring forces. Restoring forces are nothing but tensions. Which is proportional to elongation or compression from natural length. So this is how we represent a spring, a coil. So when you say natural length, that means the spring is neither compressed nor elongated. Springs ka idea is pretty simple. If you pull the spring by X, the spring will pull you back. If you push the spring will push you back. So if you look at the forces here, the force due to a spring is minus of K into X bar. Can you see? Because F and X are both are opposite. The negative sign indicates opposition. So basically, this is your elongation. This is your compression. So if you push the spring, it pushes back. So unlike strings, right? Spring can push and pull. And what does this K tell you? K here, the proportionality constant is called spring constant. The physical significance is higher the K, more difficult to deform the spring. So a spring with a higher K is more difficult to compress or elongate. It requires more force. Have a look at this. Clear? Any doubts? Turn in the page.
Oh, sir, just a minute. Yes, sir.
Combination of springs. We're going to use this again in SHM primarily, but we should know this for a few problems. Springs in series. So if you take a spring and if you take a spring, K1 and K2, you can replace this with one spring, K equivalent, where 1 by K equivalent will be 1 by K1 plus 1 by K2. Be careful, this is opposite of resistors. So when they're in series, they have same tension. And if you say elongation is x1 and x2, x1 and x2 are elongations. So we have K1, x1 should be equal to K2, x2 should be equal to K equivalent x1 plus x2. This is how it is derived actually, but this result is more important. It is reverse of formulas in resistors. If the strings are in parallel, you can think about it logically also, right? If the springs are in parallel, they will work together, so you'll get more force. When they're in series, if one spring is weak, doesn't matter how strong is the other guy, the whole thing will mess up. You're getting? If you put a strong guy and a weak guy in a line, right, you can pull as strong as the weak guy, isn't it? The statement goes like this: the chain is as strong as the weakest link. You getting the point of the statement? So in this case, K equivalent would be K1 plus K2. So here springs will have same elongation. Have a look at this. Clear? This we use a lot in simple harmonic motion. Here we will not use much, but the next concept, there are a few problems where we'll see later on. Next thing, turn in the page. What happens if you cut a spring? Now the spring constant K is actually given by YA by L. That means if you take a spring here, we are talking about this area. Basically, how thick is that wire which you are using? This is the cross-sectional area of the wire used to make the spring. Means if you use a thick wire, spring will be stronger. That is your A. Y is called Young's modulus. Let's not worry about it. It tells you how strong is the material. Example, Y of steel is greater than Y of plastic. L is length. So whenever you cut a spring, material won't change, area won't change. Agreed? So K into L will be Y into A is constant. So whenever you cut a spring, the spring constant increases. Meaning, if you take a spring K and length L, don't remember this thing. Later on, we'll do a problem on this. And if you take a thing and you cut it here into L1 and L2, let the spring constant becomes K1 and K2. So when you cut this, you get two pieces. K2, L2, K1, L1. So from the formula, we get K1, L1 is equal to K2, L2 is equal to K into L. The product K into L will remain constant. Example, let's say K and L. I cut this into L by 3 and 2L by 3. Let this be K1 and let this be K2. So from the formula, we get K1 into L by 3 is K into L. So K1 is 3K. So when you cut the spring, smaller springs actually have more spring constant. K2 into 2L by 3 will be again K into L. So K2 will be 3K by 2. So whenever you cut a spring, the spring constant actually changes. K is not constant for the given spring. It depends on the length. Have a look at this. So if you make the wire thick wire, A will increase, therefore K will increase. If you use a stronger material, instead of using a plastic spring, if you use a copper spring, it is stronger. More than copper, steel ka spring is even more stronger. So that depends on the material. We are not interested in Y and A right now, but that L is important, K into L. If you cut a spring, what happens? Please check this page. Have a look at this example. Quite important. Huh? This will come a lot in a chapter called SSM, but we are going to use here also. Clear? Let's see a question. So there's only one thing that I taught you. F is Kx. So if you pull the spring, it will pull back. If you push the spring, it will push back. Just give me a minute. Let's say problem. We have a spring, 2 kg, 3 kg. K1 is 100 Newton per meter. K2 is 200 Newton per meter. Find elongation each spring. In the second case, right, we have multiple springs there. If you release it from natural length, what is the distance moved by the block M? Let's get this. First one is easy. See the first one. You can just treat this thing like, if you take this whole thing as one system, this force will be K1 x1 and this whole weight will be 50. So K1 x1 is equal to 50. So that would be 100 into x1 is 50. X1 is equal to half. Now, if you just take the 3 kg as one system, this force curve will be K2 x2 by 30, and you will get K2 x2 is equal to 30. X2 will be 30 by 200. You don't want to do take the whole thing as one system. See, this is how the FBD will look. This guy will be K1 x1. X1 is the elongation. This spring will also pull K2 x2, and this will be 20. So you can write K1 x1 is equal to K2 x2 plus 20. Same thing. Check. This is how you can write FBD for each system. Because the springs are stretching, they will pull. So this spring will pull up. This spring will pull down and this pull up. So it will always pull. It will pull both of them inside. Please check. Or if you get confused, right, what you can do, simply replace them with ropes, find the tension. Tension is equal to kx. So the idea is the same. All clear with this? Easy? Please check. Anyone confused, please ask. Get the second question.
So can you go back for a minute?
Mhm.
Yes, sir. Thank you. So if you leave this from equilibrium, how much will it come down in equilibrium? Get this easy one. You just have to find K equivalent and your job's done. You can replace them with 6K, 2K, and K. And you can replace this with one spring, K equivalent. So this is mg. This would be K equivalent into x. So K equivalent into x is mg. X is mg by K equivalent. And 1 by K equivalent, all are in series, is 1 by K, 1 by 2K, and 1 by 6K. This is 3 by 2K plus 1 by 6K. Check. 5 mg by 3K. That's your answer. Okay, questions can be framed like that, equivalent springs. If these three are in parallel, 6K, these two are in parallel, 2K, then this is K and all three are in series. Just like, resistors which you have studied. But here formulas both are reversed, so just be careful about that. All clear with this? Next one is a good one. Any doubts on this? Can I turn the page? Hi, Ritu, clear now? Ali? Arjun? Neil? Ritu, there?
Yes, I'm there.
Okay, next one. So we got a wall, we got a spring.
spring is K and length is L. So somewhere in the middle here, at point A, which is at a distance of 0.2 L and 0.8 L, you're not catching the end of the spring. You kept something like this, a rod kind of thing, and you're pulling with force F. A point A on the spring is pulled by a force F. Find the distance moved by the point A when the system is in equilibrium. Normally pulling the end of the spring is fine, we know that, but what if you pull in the middle of the spring somewhere? Find the distance moved by point A when the spring is in equilibrium. Means you're slowly pulling it and finally it comes to rest. And you're applying force F, so ideally speaking, it will start oscillating. Let's ignore all that. We'll not get into that stuff. बाद में करते हैं oscillation वाला, that comes in work per energy. How do you do this? If you pull on the edge, so the story was easy. F is equal to K into X, question ho gaya, khatam. But I'm not pulling on the corner. I'm pulling somewhere in the center, somewhere point to it. Think. It's a good one. And just to give you a little brief, when you pull this way, can you observe this part is compressed? This part is elongated. Observe किया? पूरा spring elongated नहीं था. The right part is getting compressed, the left part is getting elongated. L by 5 to the right, okay. You got such a good answer. I was not expecting that. I don't think you'll get such a good answer, Anika. उसमें तो F तो है ही नहीं. How did you get an answer without F? It's a blunder. So Jana, L by F means what? That is point to L, right? Meaning this force will go and stick to the wall. The answer is a blunder. Others try, you got a minute. Think how to proceed with this. Then I'll give you a hint. See, I'll just give you an idea. Because the two springs are getting split. Can you just treat them like this, two springs? Just treat them as two springs, K1, 0.12, and this is K2 and 0.8L. Find the new spring constants. So you have created two different springs basically. You literally cut the spring at point A. That's what you did. Now think how to proceed from there. Now try, I'll give you a minute more. So cut the spring at 0.8 here, get the spring constant of this part, find the spring constant of this part. It won't be K anymore, it has changed. No, Arjun. I think वो नहीं है. No, that's not the answer. Right, Adrit. Ronak, you're wrong. Ranjan, you're wrong. See. This is 0.8L. Let's call this guy K1. Let's call this thing 0.2, this thing 0.2L. You can clearly see here the right part is compressed and the left part is elongated. You can't use a regular string formula. The right part is compressed. Left part is elongated. So treat them like two different springs. So this is how we will draw. Just put a block there or something, just for our understanding. Let's find the spring constants also. K into L is equal to K1 into 0.8L. So K1 will be 5K by 4. K into L is K2 into 0.2L. K2 is 5K. So the whole question becomes as if you have a spring of 5K by 4 and 5K like this. And now when you're pushing it, let's say this thing has moved by X. Now, if you draw the FBD of this block, this spring is pushing with 5Kx. This spring is pulling with 5Kx by 4. And this force is F in equilibrium. So F is equal to 5Kx plus 5Kx by 4. Take out 5Kx common, you end up with 1 plus 1 by 4, that is 5 by 4. X is equal to 4F by 25K. Check your answer. That's what happens if you catch in the middle of the spring and pull. You just cut the point wherever you want to, pulling there, and you get two springs, find the spring constants and finish it off. This is the reason you should know what happens if you cut a spring. K ka value will change. Equilibrium problems. Do have a look at this. Any doubt? Anyone not convinced with this, please ask. And if you're thinking, sir, when you cut the spring, why is it, becoming K more? Logically, so if you have a long spring with a lot of coils, okay? If you stretch this by, let's say 1 centimeter, example, and let's say there are 10 turns, means each turn will take 0.1 centimeter elongation. But what if you have only 2 turns? Means each turn will stretch by 0.5 centimeter. Isn't the wire got more stretched? It is under more tension, isn't it? That's why the spring constant will be more. So the longer the spring, you can pull more easily. Is this clear, everyone? Got this? Next one. Can I turn the page? Now I can just change the position at different points and I can ask you. You can just treat as if there is a block in the middle and solve. Clear now, Mehan? Swastika? Ronak? Clear? Udayan? Got this? Maulika? Aryan? Yasha? Clear? Perfect. Next one. Let's say we have a spring balance. What does the spring balance measure? What does a spring balance measure? Be careful. It measures tension in the spring, but it shows tension by G. So you can just remove the spring balance and pick up, put a rope and find the tension. And it shows the reading tension by G. Just like, the weighing machine, it measures normal reaction and shows tension by G. Getting it? Spring balances don't measure mass directly. They measure tension in the spring. Find the reading of the spring balance. Get them, easy questions. Find reading of the spring balances. You can start doing HCV. If you have not done before, finish off your HCV. You can finish your PACE booklet and you can start doing, see, if you're doing your PACE booklet completely end to end, you can directly start doing level 3, level 4 of my booklet, and you can go for level 5, level 6 for, higher level problems. Level 5, level 6 are difficult, right? But they'll give you a good practice, and it is not like you have to complete everything. Level 3, level 4, you can complete properly, PACE book completely. Level 5, level 6, maybe you can, you can do every day like 3-4 questions, or weekly you can do 15-20 questions. That will be a good way to do that. Instead of sitting and trying to do the entire thing in one go, you can spread out level 5, level 6 whenever you want to do revision kind of thing. But your PACE booklet and level 3, level 4 of a booklet should be minimum done. If someone is finding PACE booklet difficult, then you can go for level, theory bits, level 1, level 2, level 3, level 4 of my booklet. The only reason, the booklet I gave you is little better is because the questions are segregated. PACE booklet mein kaisa, it is all scattered. There is no subtopic wise division. But if you look at my booklet, you'll have division like equilibrium ka problems alag hai, forces on a horizontal alag hai, incline alag hai. So you'll get that variation, nothing much. So you can stick to any one booklet. Again, I'm saying choose 2 books and finish off properly. Yeah, the first 2 are right. Get the C part. Right, Rona. Hanika, you did a classic mistake. That means if we tie you to 2 elephants and pull you with equal force from both the sides, you'll be safe and sound and you'll feel very comfortable. Whenever someone says tension is zero, remember that is the meaning of it. Imagine yourself tied here. This side we tie 100 tons and this side we tie 100 tons with equal weight. Since the weights are equal, you'll feel nothing. क्या था first part? A and B both have same tension. No, Ali, it won't show 100. It will tension is 100, but it will show 10 kg, 100 by this thing. How to do? See, you just need to find the tension in the string. Tension 100. System is in equilibrium. Tension is 100 Newton. Therefore, reading will be tension by G, which is 10 kg. Here also, tension 10 kg. It is at rest because both the sides it is equal. So here also tension is 100 Newton. So here also reading is 10 kg. It won't show 20 kg. It won't show 0. Be careful. It will show the tension in the string. Remember, are you forgetting it? Kya? यहाँ पे भी है ना tension T. The wall is also pulling with equal force on the left hand side. अरे, that horse का story I told you na. Isn't it the same problem? You pull with both the sides or you pull with one side. The other wall is playing the role of the tension there. What about this guy here? Tension. This will be 100. This will be acceleration. Here system won't be at rest. Tension 50 and acceleration. Write the equations. T minus 100 is equal to 10 into minus A. T minus 50 is equal to 5 into A. Solve these two equations. You get T is equal to 50. You want to eliminate A, no? Just divide them. If you just divide them, you get T minus 100 by T minus 50 is equal to A will cancel, you get minus 2, cross multiply. You get T minus 100 is equal to minus 2T plus 100. T is equal to 200 by 3. Therefore, reading will be T by G 20 by 3 kg. Check. Arjun, the second part is wrong, right?
Yes, I
Ronak,
made
you, yeah, Ronak, you also got the third part wrong. Check where it went wrong. It's not average. I didn't see that. You have to find the tension in the string and divide by G. See, whenever you get a spring balance, now, if you're getting confused with the spring balance, just usko ignore kar lo. Just put a string there, find the tension in the string, and then divide by G. That's it. Spring balance is nothing. It doesn't do anything. It just measures the tension in the string. Please check. Easy question, standard one. Clear? Can I go ahead? No. Any doubts on this? Next one. This is an important concept. tension in springs and strings. Net force, you can use net force method for third part. Acceleration aa jayega. Actually, if you think about this thing now, isn't this as good as this problem? Atwood machine था वो. बस सिर्फ दो पुली तो it looks confusing. You could have written directly 2m1 m2 by m1 plus m2g for tension. It's really not that different. Except for that pulley in the middle, I stretched it little more. Tension in strings and springs. Listen carefully. It's one. So what this thing is, let's take an example and see from there. Let's say if you have a spring, and let's say you keep a block of mass in. So initially the tension in the spring, kx, this is mg. So you will get kx is equal to mg. Now, if you take another block of mass m, and if you just try to attach this, what happens is suddenly the weight has become 2 mg. The spring force kx will still remain mg. The spring doesn't care. The spring will say, the spring force is what? F is k into x, right? When you kept the block, did x suddenly change? No. So the moment when the block is attached, the x does not change. It will change. You have to give some time. When block is attached, elongation does not change suddenly. So spring will exert kx only. And because of this, the whole setup will go down with some acceleration. So this is the thing about a spring. Spring does not care with what force you're pulling. Spring will say only one thing. Mera elongation xf, so force is k into x. I don't care you pull with 100, you pull with 1000, I will exert k into x only. But the same thing, if you do with a string, tension, mg, the moment you take a block, and if you try to attach it, since the string cannot stretch, acceleration is 0. This is the difference between the string and spring. Springs can stretch, so acceleration need not be 0. Therefore, suddenly the tension T dash becomes 2 mg. So tension suddenly changes in the strings. This is the main difference. Yeah, spring weight will remain as it is initially. When it thoda time diya it will stretch, but at that moment it will remain same. This is a major difference. Right? In springs, the tension can change, whereas in springs it will take time. This idea is quite important. Have a look at this. Means if you take a spring and let's say you apply 100 Newton, elongation will be 100 Newton ka force. Suddenly, if you make it 1000, spring doesn't care. It will still give 100 only because it will take some time to respond and stretch. Whereas strings are not like that. The moment you go from 100 to 1000, suddenly the string will become more tight and you'll get 1000 immediately. This happens because the strings cannot stretch. They're inextensible, ideal strings. All clear with this? Can I turn the page? Clear. Now, Aryan, go ahead. Now, in this, now again coming to springs, what happens if you cut a massless spring? Now, in our portion, we have only springs without mass, but let's study a bit so that you will know. So, if you take a spring with a block M, and let's say you take a scissor and you cut it, what happens is when a massless spring is cut, there is no inertia there, meaning it cannot stop the thing from moving. Since it is massless, it immediately comes to the natural length. That means tension becomes zero suddenly. But in real life, you won't find massless springs. And tension becomes zero. That is because when you say F is equal to MA, right, and M is zero here. So the moment you cut it, right, if there is a force, acceleration would be F by M. This will tend to infinity if there is a force. You get an infinite acceleration for that point when you cut it. Immediately it goes to the natural length. What happens if you have a spring with mass? This is how real life works, but again, we don't have problems with mass with springs. So let's say you cut it here. The moment you cut it here, if you observe, the block doesn't care. Actually, the block just remains there at the same place. Whereas this point started traveling down because of the force. The block still remains there. The point is still traveling down. Now, when you have come to the natural length, let's say this is the natural length now. The block won't move until the spring comes to natural length. And now the block will start falling. And the spring will remain in natural length. The reason, the mass of the spring, right? Because of inertia, you get a finite acceleration. It will take some time for the spring to come to natural length. When the spring has come to the natural length, tension becomes zero, and then this thing starts falling. But we don't have this in the portion. We will not study these cases. But then again, they can always ask this as a theoretical question. Look at this thing. That's a slinky. I'm sure you must have played with it. So that is like a kind of a spring here. Observe this. Did you see what is happening? Niche ka part dekho. Huh? See that again. When he's leaving the spring, now this is a slinky, which is like a spring with a mass. And when you leave it here, see what happens. Did you observe the bottom part is not moving at all? Until unless the upper part comes down, it won't move. See. Now it moves. This is what I was saying. So the people are trying with a bigger slinky there. Look at this thing. Everyone can see?
Yes,
So
sir.
look at you observe the bottom part here, okay? It doesn't move only. Why is the music so weird, right? Now it moves. This is a bottom view. The reason why it is not moving, right? The bottom part of the spring is still stretched. That elongation is balancing the weight of the lower part of the spring. Because you have mass, it takes time for it to move. If it is massless, it would have just moved in an instant. You won't be able to see that in real life. So
So this is the modelling that I've been doing, and so this was done with the don't collapse instantly.
So how did
clear with that? So there, I'm just not bluffing. It is true. Clear with this? But then again, we don't have this in the portion. We'll be sticking to massless strings. Any doubts on this page? Please ask. All clear? Let's see a question. Remember massless springs. So all are if I don't mention anything, it is massless springs. So springs with mass and springs without mass behave differently. So what happens if you A is here and B is here? Two different questions. Find the acceleration of the blocks when it is cut at A and cut at B. Case 1, you're cutting at A, then find the acceleration of M into M. Case 2, you're cutting at B, find the acceleration of M into M. Two different questions, two different accelerations. 4 answers. Try. Remember the only concept I taught you, if you cut the spring, uska tension 0 hoga, baki springs ka tension change nahi hoga. That's it. That is the only concept. Whichever spring you cut, that guy tension will be 0. The other springs don't care. So if I have to write the steps now. Step 1, find tension in the springs in equilibrium. Step 2, the spring which is cut will have 0 tension. Other springs are unaffected. Step 3, use 0, F is equal to MA to find the acceleration of the blocks. Acceleration, right? Palaksh, you're finding, okay, you got it. You're right. Think for a minute, I'll show you then. Step one, finding the tension. So here I'll just call this thing T2, which is 2 mg. I'll just call this T1, which is 3 mg. So the first case A, when you're cutting at point A, the tension T1 becomes 0, T2 will still remain same. बस वही idea था. Now draw FBD of the block M. There is no tension only on the top, T1 is gone. Bottom you have mg and T2 will pull springs because it's elongated, it will pull. And T2 is 2 mg. So acceleration of M will be mg plus 2 mg, it will be 3g. Whereas for the 2m block, this is T2, which is 2 mg. The weight is also 2 mg. So 2m will say, I don't know what the hell is happening. It is at rest. It doesn't care. That's how you do. Same thing if you do for B. Now you're cutting at B, so T1 will remain same. T2 will become 0. That is the idea. Whichever you could make that 0, remaining tensions, keep it as it is. Now draw FBD of the blocks. M. This would be T1 3 mg. Your own weight mg. T2 is 0, so this guy will go up now. So acceleration of M will be 3 mg minus mg, 2 mg by M, 2g upward. And for 2m, tension T2 is 0 and your weight is 2 mg, so you'll just fall freely with g. Please look at the cases. Step 1, find the tension in the springs that you know from equilibrium. This tension will be 2 mg, this tension will be 3 mg. Step 2, if you're cutting at A, make tension in the A ka spring 0, when T1 becomes 0. If you're cutting B, T2 becomes 0. Then just draw the FBT and finish it off. All clear with this? Making sense? Any doubts? Anyone not clear with this, please ask.
So can you show the steps for a minute? Yes, no, thank you.
Can I go ahead? Next one. Next one. Let's see similar one more, little slightly more complex. This is point A, this is point B, and this is point C. There, find acceleration of the blocks when it is cut at ABC. Similar question, no, but I just made 3 points and 3 blocks. Get this, the process is still the same. Just give it a try. I'll get some water and come. Let's see. Right, Adrit. That is right. Keep going. Get the rest. See, step one. Let's call this guy TB, which is 5 mg. Let's call this guy TC, which is 3 mg. Yeah. What about TA? I don't care. TA is not a spring. A is not a spring. We don't care. A ka tension can change anyhow it wants. We don't care about A. Be careful there. So when you cut at A, look at the scenario. The moment you cut it at A, the tension in A becomes 0. That much I know. Then TB will remain same. TC will remain same. So if you look at the FBD of M, this guy became 0, but the upper tension TB is 5 mg. So 5 mg and your own weight mg, 5 mg minus mg, 4 mg. So this guy will go with an acceleration of 4g. For 2m, you have tension TB, you have your own weight 2 mg and your own weight TC. This is 0. And for 3m block also, it is 0. They don't care basically. The springs will remain same. If you cut it, the answer is 4G 0 0. Please check. What happens if you cut it B? I'll just give you a hint there. See, when you cut it B, TA, I don't know. That's the first thing. Tension at A can change immediately and we don't know. It won't remain same. If you have taken it as same as before, you are doing a big mistake. You don't know. That's the first thing. TB will be 0. TC will remain same. अभी कैसा करना है? Only springs have that property. If you remember the steps, what did I say? If you cut a spring, that tension is 0, other springs will remain same. I never talked about a string. Strings are quite weird. The tension can change suddenly out of nowhere because something happens. Now, how do you proceed from here? TA value we don't know. Think like this. A, this guy TB is become 0. This is mg. What is happening here? Do you think that string can push? Since string cannot push, the block is trying to compress the point A. It becomes slack. TA also becomes 0. So this will just fall with G. Are you getting this? The moment this thing falls here, this string here, it becomes slack like this. Tension at A is 0. It's not a rod. It can't push. But if you have taken the previous value, TA is equal to, that 4 mg and so on, you'll get a wrong answer. So be careful. Tension in the strings, we don't know. You have to draw an FBD and you have to see, is the string being pulled or stretched? What is happening? For B, this is 0. Your own weight 2 mg. And this force TC is 3 mg. So acceleration will be 5 mg by 2, 5g by 2. And for 3m, acceleration will be 0. Please check. So whenever you cut a spring, what happens to the strings? You don't know. Get the C part. So A will fall down with G, B will fall down with 5g by 2, and the third will be at rest. That might be right, Adrat. Dekhte. Try, got a minute. Look at the C part answer. What happens if you cut it C? The moment you cut it C, TA, I don't know. TB will remain same. TC is 0. So start from C. TC is 0. So this is 3 mg. So you will fall with G. For 2m, this guy is TB 5 mg. Your own weight 2 mg. So acceleration of 2m will be 5 mg minus this thing, 3g by 2. And for this m guy, this tension TB is 5 mg, which is definitely greater than the weight. Since string cannot stretch, it won't move. So whatever additional balance force you have, the TA will balance here. You cannot find the value of A initially without doing the calculations. I know if you have done that, luckily you'll get the answer, but that's not the right way to do. The answer would be 0, 3g by 2, and g down. Yeah. Please check the steps. Any doubts on this? Clear? Turn the page. Malika, clear, na? Abhinav, Venkatesh, so far clear?
Yes.
Rehan, Aryan, Ritu, clear so far? Okay. Next one. There, that is what happens when you cut springs. So let's say this is T and it is cut here. Find the tension in the string T before and after cutting. Just before and just after cutting. This point is it. Let's get this. Okay. The first part was easy. So before cutting, this was theta, theta, and theta. If you take this as T and this as T, we get the vertical components. T sine theta and T sine theta. And this is mg. So 2T sine theta is equal to mg. Tension will be mg by 2 sine theta. This is the case before cutting. Right? Now, after cutting, this is how the block looks. This is still theta. This is still theta. Now, this is what people do, okay? This is tension, and if you divide them into components, we get T sine theta, and this is equal to mg, and they do this thing. T sine theta is equal to mg, and T is equal to mg by sine theta. This is wrong. This is a blunder. Why is this wrong?
Tension has
Yeah.
changed.
Tension has changed. So चलो वो T dash ले लेते हैं.
Theta
right,
is
right.
changing.
नहीं at that instant ना immediately ना अभी theta change नहीं हुआ. Problem क्या है ना? This is the catch. The moment you cut, this block here is actually going in a circle, isn't it? It is not an equilibrium, right? So this block actually has it cannot go in this direction. it has an acceleration in this direction. Since string cannot stretch, the block moves tangentially. The reason why this is wrong is because there is a vertical component of acceleration which we are ignoring. The block is swinging and it is going down. There is a vertical component of acceleration which you are ignoring. So in this problem, it is preferable if you can choose this as your y and this is your x. Now, if you draw the FBD, you can clearly see this is tension, this is mg, that is theta, this is theta 90, so this is 90 minus theta. So this component will be mg cos 90 minus theta, which is mg sin theta, and this component will be mg cos theta. And this is what is providing that acceleration A. So tension will be mg sin theta. You have to take the forces along the string, and mg cos theta will generate acceleration ma. So the block will swing with an acceleration of g cos theta, and the tension would be mg sin theta. Be careful, both are not same. You see, we're getting mg by sin theta. This is mg sin theta. Are you getting the mistake, everyone? If you want to write in the vertical direction, na, actually equation ऐसा होना चाहिए था. mg minus t sin theta is equal to may. That would have been right. You are ignoring this acceleration ka vertical component. Be careful here. You're supposed to take the forces along the string here. Springs would be a difference. It won't go in circle then, Volika. All clear with this? It behaves like a pendulum, right, Arjun? All clear? Try this as a homework. Next class we'll discuss. Same thing if you had actually two springs. And if you're cutting here, find acceleration of the block just after cutting. You will lose in the next class. And let me just add one more problem. Did everyone try the last class homework problem I gave? That big pulley and all. Didn't try, make sure to try. Next class we'll discuss that also. All surfaces are smooth. Find the acceleration of the wedge. Make sure to try them and come. Next class, we have done almost. Next class, we'll start with pseudo force. It's not much, it's a small topic. Like I said, you could have done all loss of motion problems without pseudo force. But it is quite useful in circular motion. So for that sake, we will learn it, and I'll show you a few examples, but we really not, I don't really prefer with pseudo force. It just takes away all the understanding from you. But okay, with this we'll wrap up. So next class, we'll wrap up in the maybe another half an hour, 40 minutes. And then we'll start off with friction in the next class. So next class on Wednesday, we'll have it as usual, same time, right? So Okay. So with this, we'll wrap up for that day. So next test, laws of motion is already online. The kinematics results will be posted tomorrow. This test will be online till next Thursday. So make sure to give it Thursday night 11 p.m. I know sometimes I'm keeping it as 11 a.m. by mistake. So do inform if it gets expired before that. So any doubts in today's class?